carbonic acid as a result of carbon dioxide, but if it's like cherry Coke, then there's going to be citric acid with it. Hold on, let me hit share screen, desktop 2. All right, substance that reacts with zinc to produce hydrogen gas is what? Well, it turns out that acids react with metals. So, and that reaction is zinc plus some kind of an acid. And you don't know what kind of acid. It really doesn't make a difference. But maybe it's like HCl. And as a result of that, we get like some kind of salt. And here it would be zinc chloride, ZnCl2, because zinc has a charge of 2, it turns out, plus hydrogen. And hydrogen is H2 gas. So metals react with acids to produce a some kind of a salt and usually hydrogen gas. And to balance this, it's got to be a 2 here. So anyway, metals react with acids. Metals don't react with bases, but they do react with acids. So that can also go in the Venn diagram thing. Substance is what? If it feels slippery and tastes bitter? Well, the slipperiness from a base is actually from that saponification reaction that I described. Bases react with lipids, which are oils, fats, waxes, and greases, to form a soap. And the reason why bases feel slippery is because you're actually like making soap with your the oils in your skin and with the base. And the bitter taste, like people describe bitter a couple different ways. Like you might say, oh, there's some food that's kind of bitter or something. People sometimes describe like unripe fruit as bitter, which is kind of correct. But the description about bitter is more like the flavor of soap, which is not something you should be tasting. It's disgusting. Anyway, a compound that reversibly changes color in a solution, whether it's in contact with an acid or base, is an indicator. So those indicators are the colored solutions or colored chemicals which change color. Now, in solution could be like phenolphthalein, where you actually put it into water, but also when you use litmus paper, there's a solution that's formed on the surface of the paper where the indicator goes into solution with the water that you put on the paper itself, and it'll change color. So an acid, does it taste sour? Yep. Turn litmus paper from blue to red? Yes. Conduct electricity in water solution? Yep, they're all correct. So it turns out those are all properties of acids. If you were to mix equal amounts of acids and bases, which of the following, or both of which have the same concentration, what would be the product? So if you have some kind of an acid, which is H with something, so maybe it's sulfuric acid, H2SO4, and you react it with some kind of a base, maybe sodium hydroxide, NaOH, you end up forming water, H2O, and then whatever's left, so it'd be sodium sulfate, Na2SO4, something like that. So what you get as a result of an acid and a base is a water and salt. So this is the acid. You know it's an acid because it starts with hydrogen. You know this is a base because it ends with the OH. Here you get water, and then some kind of a salt. When we say salt, it's an ionic compound that you write the formula based upon what's on the ion chart. So you get salt and you get water. So usually when you say salt, people talk about table salt, and that's sodium chloride. But to chemists, salt isn't just limited to sodium chloride. It's any ionic compound that is made of an anion and a cation, and balance the charges and go from there. All right, so those are things that are true. Let's see, and then substance with a sour taste. So like we usually describe those as being acids, and it actually turns out that if you buy Sour Patch Kids, most of the flavor is like that it's very, very sweet, but the powder on the outside of Sour Patch Kids is citric acid. So it's actually like a gummy, and then they coat the outside with citric acid. So you're getting like a fresh blast of citric acid straight up. It's a solid on the surface, but then as soon as it comes into contact in your mouth and forms a solution, it's a strongly acidic solution. Red litmus paper turns blue in the presence of what? So red means acid. Red litmus paper changes blue when it's in the presence of a base. So you can identify which of these things are bases. Well, lemon juice is from a fruit, so that's an acid. Vinegar is acetic acid, so it's not that. Sodium chloride is an ionic compound that's just a neutral thing, NaCl. There's no OH or H, so it's not sodium chloride. And it turns out baking soda forms a base whenever you have it in the presence of water. So the molar amount of an acid or base in solution compared to the amount of water is the what of the acid or base. Okay, there's some confusion about the difference between strength and concentration. What the strength of an acid means is whether or not the ionic compound completely dissociates in the water or not. And if an ionic compound completely dissociates, we say it's a strong acid. If it doesn't completely dissociate, it's a weak acid. And I showed you the formula to calculate whether it's strong or weak based upon the ratio of hydrogens and hydroxides. What matters is what is the concentration. What you're talking about is what's the molar concentration of hydrogen and hydroxide in solution as compared to that of water. So whether or not an acid is a strong acid could be of a small concentration. In other words, you could take hydrochloric acid, which is a strong acid, but have a very small amount of it in water, and the acid is still strong, but the concentration would be low. How much ends up reacting depends upon the molar concentration. So concentration is the best thing there. In a neutral reaction, an acid reacts with a base to form water. That's true. And also a salt. So it is both A and B, so E is the right answer. The thing is, you have some kind of an acid, like I wrote before, maybe, I don't know, hydrobromic acid, and maybe like, I don't know, calcium hydroxide, whatever, BCaOH2, would make water, and calcium bromide, Ca, that looks like a G, CaBr2. All right, that looks okay. When an acid reacts with a base, whether the resulting solution is an acid, base, or neutral, that depends on the concentration of the acid and base used. In every reaction, what's important is that in order for neutralization to completely take place, the quantity of hydrogen ions and the quantity of hydroxide ions has to be the same. The number of moles of hydrogen and the number of moles of hydroxide have to be equal. And if the moles of hydrogen and moles of hydroxide are equal, then you get a complete neutralization reaction. If there's more hydrogen than hydroxide, then there's hydrogens left over and the product is acidic. If there's more hydroxides than hydrogens, then the product is a base. And in the titration reactions you did, it's all about whether or not you have the quantities of hydrogen and hydroxide equal. Okay, name some of these acids and whatnot. So there's some binary acids, and the binary acids include the HCl and HI. And the binary acids are called that because you have just hydrogen and then some kind of a cation. And in that case, well, you know to name this a couple different ways. HCl, if it's not an acid, you would call it hydrogen chloride. And this compound is a compound when it's not in solution. It turns out that it's a gas called hydrogen chloride. But as an acid, this should say as, not add acids. Name them as acids. As an acid, what you got to look at is the chlor, and then for binary acids, it's always the formula hydro, and then something, ic, acid. And what goes in that space is the root of the name of the element. So HCl is hydrochloric acid. And similarly, HI, so I is for iodine. There's this iode. It's the root of the name of the element. So instead of hydrochloric, it's hydroiodic. Hydroiodic acid. And then for HNO3 and H2SO4, those are oxyacids. We identify them as oxyacids So the green ones are oxyacids, and the blue ones are just binary acids. Oxyacids, you look at the name of the anion. Here, NO3 is the nitrate anion, and in the naming scheme, the 8 changes to an ic. So the 8 changes to ic. So this, instead of nitrate, it's nitric acid. The SO4 is the sulfate anion. So instead of 8, that changes to an ic. But sulfur is one of these exceptions. We don't say sulfic, but sulfate comes from sulfur, and it's sulfuric acid. So, you know, we name stuff back in February or so. And then hydrobromic acid, it has the hydro and ic, so it's related to brome, and that's bromine. On the periodic table, bromine is a group 17 element, so it has a charge of 1, like 1 minus. So if you put a hydrogen, which is H1 plus, with a bromine, H1 minus, it's just HBr. All right, so a titration reaction. You got a volume and a molarity for the acid. This is the volume and molarity for an acid. We're going to titrate it with some unknown concentration of a base. Some volume of an unknown concentration of sodium hydroxide. The formula that's true is that the molarity times the volume for the acid is equal to the molarity times the volume for the base. So if you have a volume and a molarity for the acid, that's equal to the volume times the molarity, unknown concentration of the base. What we're trying to figure out is what's the molarity of the sodium hydroxide. That's the base. The molarity of the base is equal to the molarity of the acid times the volume of the acid divided by the volume of the base. So if you take the molarity of the acid, 2.5 molar, times the volume of the acid, 25 milliliters, and divide that by the volume of the base, 40 milliliters. And in this problem, we have 2 significant figures in the 2.5 molar, so it's appropriate to have 2 significant figures in that concentration. It comes out to be 1.6 molar. You know that it has to be less than 25 or 2.5 molar because the quantity of sodium hydroxide we needed was larger than the quantity of hydrochloric acid that was used. And because there's a greater volume of sodium hydroxide that was needed, the concentration of sodium hydroxide must have been less. And it comes out to be 1.6 molar. Okay. Let's see. Solution's got a pH of 2.3. Is it an acid or a base? Well, it's an acid. That's easy to tell because acids have a pH less than 7. What's the hydrogen ion concentration? So the formulas that relate pH and hydroxide concentration are that the hydroxide concentration is equal to 10 to the negative pH power. If I take 10 to the negative 2.3 on my calculator, it's probably about 5 times 10 to the negative third, 10 to the negative 2.3. Yeah, so on the calculator it says 0.0050. We're going to have 2 significant figures. But typically with concentrations for acids and bases that are small, it's good to write it in scientific notation. Your calculator might also show you 5.0 and then a whole bunch of stuff. And then over on the right-hand side, say E negative 3. And the E negative 3 means times 10 to the negative third. So it's good to write this concentration as value in scientific notation, 5.0 times 10 to the negative third, and the unit is molar. And what is true is that the absolute value of the exponent in the concentration is always within 1 of the value of the pH. In other words, this 2.3, that's within 1 of the number 3. Not like negative 3, but just 3. Oh, I touched it. let's see. I got to push a button, I think. There we go. The screens are kind of connected and it's not working right. All right, solution's got a pOH of 7.4. Find the hydroxide concentration. So there's a relationship between pH and pOH. pH plus pOH is always equal to 14. So this pOH of 7.4 is the inverse log of the hydroxide concentration. If you want to know the pH, you can take 14 minus pOH value. I did it again. All right, so if you go 14 minus 7.4, 14 minus 7.4, that's 6.6. So the hydroxide concentration is equal to 10 to the negative 6.6. And you should expect a value whose exponent is, you know, around 7. It's 2.5 times 10 to the negative 7th. And the unit is molar. All right, then 6 and 7. So number 6, you got 20 milliliters of 0.25 molar calcium hydroxide and 40 milliliters of 0.2 molar HCl. Is the mixture going to be acidic, neutral, or basic? So now what matters is which of these compounds do I have a greater concentration of either the acid or the base? And one thing about this reaction is this calcium hydroxide is CaOH2. But over here, the acid is just HCl. So there's only one hydrogen, but there are two hydroxides. A smart thing to do is write the reaction out. So if I write this reaction, it's calcium hydroxide plus HCl. And the products are going to be calcium chloride, which is CaCl2, and water, H2O. That equation is not balanced. I got to put a 2 in front of the HCl. So now it turns out that in order for this reaction to produce a neutral solution, you're going to need twice as many hydrochloric acids as the number of calcium hydroxides. So what I want to do is figure out, with this volume of calcium hydroxide and that concentration, how many moles of calcium hydroxide are present. So what is true is that the number of moles is equal to the molarity times the volume. If I take the molarity of calcium hydroxide, 0.25 molar, and multiply it by the volume, and because molarity is in moles per liter, this 20 milliliters is best written in liters. That's 0.020 liters. That'll get me how many moles of hydroxide, or like how many moles of calcium hydroxide are present in the solution. 0.25 times 0.02 is 0.005 mole. So I got 0.005 moles of calcium hydroxide. And the same thing with the hydrochloric acid. If I take 0.20 molar times 0.040 mole, or liters, you get 0.008 mole of HCl. Now, at first glance, it looks like there is more HCl than there is calcium hydroxide. In other words, I got 0.008 mole HCl, but there's only 0.005 mole of calcium hydroxide. What matters in the reaction, though, isn't just how many moles of each of the chemicals are available, but what's the mole ratio of calcium hydroxide to hydrochloric acid. And it turns out that for every 1 calcium hydroxide, I get twice the concentration of the hydroxide ion itself. meaning when this calcium hydroxide dissociates, you can write it as a dissociation reaction, CaOH2. When it dissociates, you get a calcium, but you get 2 hydroxides. So this 0.005 moles of calcium hydroxide is the concentration of the calcium hydroxide itself, 0.005 mole CaOH2. And when it dissociates, I get 0.005 mole of calcium, but I get 0.010 mole of the hydroxide ion. Because for every 1 calcium hydroxide, you get 2 hydroxides. So it turns out that there is actually a greater amount of hydroxide than there is the amount of hydrogen. If you compare these two numbers, compare the amount, the molar quantity of hydroxide, there's a greater molar quantity of hydroxide ions available than there is HCl. So when the reaction is complete, it turns out that there is more hydroxide than there is HCl. And the two products aren't just calcium chloride and water. There's calcium chloride, there's water, but there's also going to be calcium ions and hydroxide ions that are left over, because the calcium hydroxide is actually like a excess reactant. It's an excess reactant also because in the mole ratio, you need 2 hydrochloric acids for every 1 calcium hydroxide. So in order to make all 0.05 moles of calcium hydroxide react, you would have to have 0.1 moles of 0.01 moles of HCl. We don't have 0.01 moles of HCl. Instead, there's only 80% of that amount. So the final solution is not neutral, but it's basic. We're going to end up with, if you were to take that quantity of calcium hydroxide and this quantity HCl, mix them together with some phenolphthalein, it's still going to be pink. The pink color indicates a base with phenolphthalein. So that one's a little bit more complex, but that's the way that goes. All right, you got 0.02 moles of sulfuric acid in 500 milliliters of water. We want to know what the pH is. So the first thing you can do is figure out the concentration. The molarity is equal to the number of moles of solute divided by the volume of the solution. Solution. So if I take 0.020 mole and divide it by 0.5000 liters, that gets you the molarity of the H2SO4. 0.02 divided by 0.5 is 0.04 molar H2SO4. But the thing about the H2SO4, this is an oxyacid that's diprotic, meaning there are 2 hydrogens in every H2SO4. So as a dissociation reaction, this H2SO4 breaks down into 2 hydrogens and 1 sulfate. So if that's the concentration of H2SO4, the concentration of the hydrogen ion, which is what the pH is measured based upon, is twice as great as the concentration of H2SO4. Meaning, if the concentration of this is 0.04 molar, the concentration of hydrogen must have been 0.08 molar, and the sulfate is 0.04 molar. The pH doesn't depend upon what the concentration of H2SO4 is, it depends upon what the concentration of hydrogen is. So when you calculate pH, that was goofy, pH is equal to the negative log of the hydrogen ion concentration. Same as the hydronium ion concentration, but here it's the same as hydrogen. So if you take negative log of not 0.04 molar, but 0.08 molar, negative log 0.08, let's see, negative log 0.08 is 1.1. So it's a pH of 1.1. So So you may have calculated it's 1.4. You'd get 1.4 if you use 0.04 molar, but because sulfuric acid is diprotic, meaning there are two hydrogens in the H2SO4, you got to double the concentration of the sulfuric acid. All right, so 6 and 7 are a little complicated because they both have either a base with two hydroxides or an acid with two hydrogens. Okay, and all this is all recorded and whatnot. So the other thing has the, what do you call it? Like the Venn diagram of properties of acids and bases. There's a whole bunch of different things you could know. Acids have a pH that's less than 7. Bases have a pH that's greater than 7. Acids taste sour. Bases taste bitter. Acids react with metals. Bases, they feel slippery, and that's because of that reaction that takes place between bases and lipids to make soap. Feel slippery. Let's see, acids, litmus is red. Bases, the litmus is blue. For acids, there's other indicators, like phenolphthalein is colorless, but for bases it's pink. In acids, there's always hydrogen ions in solution. But for bases, there's hydroxide ions in solution. Let me think. That's pretty good. You could say that like phenolphthalein is colorless, or phenolphthalein is pink. And the kind of examples for acids, you know, a lot of people think about fruit. A lot of soda is acidic. Juices. We also use acids for cleaning surfaces, for etching concrete, stuff like that. But bases, common examples include like soaps, or a cleanser, or a drain cleaner, or maybe an antacid, like Tums or whatever. And the thing that acids and bases have in common is that because you have either hydrogen ions or hydroxide ions in solution, you have ions in solution, both acids and bases form solutions that are electrolytes. And generally, especially at high concentration, both acids and bases are corrosive, like to your skin, so you don't try to come into contact with strong acids or strong bases. The biggest deal is that they are electrolytes. And the other thing that they have in common is that acids and bases react together to always form water and a salt. Like when they are reacted, in other words, it takes both an acid and a base to make an acid-base reaction take place in which salts are made. So in industrial processes, it's very common to be like, okay, I want to have this specific ionic compound that's in a very pure form. You can find the acid and the base that have the two ions that it takes to make the reaction take place, and you can react those two chemicals together to get the salt you're looking for. All right, and then on the back of that, there's some things about some different ways to think about the roles of acids and bases, and the two major definitions of acids and bases are the definition provided by Arrhenius and Bronsted-Lowry. And those two definitions describe acids and bases in a couple different ways, but the general way, hold on, where'd it go? Whenever you have an acid, like hydrochloric acid, if you put HCl into water, it dissociates into hydrogen ions and chloride ions. So acids in solution increase the amount of hydrogen that's hydrogen ions that are present in the water. So one way to define an Arrhenius acid is that you've got some kind of a compound that dissociates into hydrogen and some other kind of anion, where a base is something that's like maybe the sodium hydroxide, and it dissociates into sodium ions and hydroxide ions. So Arrhenius acids are defined as acids that increase the amount of concentration of hydrogen in solution. Arrhenius bases increase the amount of hydroxide in solution. But the thing about a hydrogen ion is it's really just a proton. Because if you think about how a hydrogen ion is made, a hydrogen ion is really a proton with an electron in orbit around it. And there's nothing more complicated about a hydrogen atom than that. So a hydrogen atom is a proton with an electron. What a hydrogen ion is that element missing its electron. So if you get rid of the electron, a hydrogen ion is just a proton. That's it. There's nothing more complicated. Whoa, yes. Maria, what's today? 20th. So the thing about the Bronsted-Lowry definition is if you have a compound like HCl and it dissociates to make hydrogen ions and chloride ions, because hydrogen ions are essentially just a proton, that a Bronsted-Lowry acid is defined as something that has protons, that can donate protons. So what it means to donate protons is that there's a proton that's available that can react with something that is an anion. And in the case of acid-base reactions, if you think about the neutralization reaction, where you have hydrogen ions and hydroxide ions that form water, H2O, the Bronsted-Lowry acid definition is that in order for this, one way to think of it is in order for this neutralization reaction to take place, where hydrogen and hydroxide ions neutralize each other, in order for the reaction to take place, the hydrogen ion has to be present. And what donates the hydrogen ion to the reaction is an acid that has donated a proton. And you can also think about Bronsted-Lowry bases then as proton acceptors. We call them proton acceptors in the sense that this base, the hydroxide ion, accepts the hydrogen ion to react to form the water molecule. So they're just different functional definitions of acids and bases. There's also another definition of acids and bases called Lewis acids and bases. That's a topic not for this course, but for AP Chem. So neutralization reactions take place when hydrogen ions and hydroxide ions react to form water. So generically, acid-base neutralizations take place when the hydrogen from an acid and hydroxide from a base are in equal concentration and form water. The water is neutral. Binary acids are acids that are like formed between hydrogen and then some kind of an anion, usually from group 17, typically like chlorine or bromine or iodine or fluorine. And in that case, it's just like HCl or HBr, something like that. Oxyacids are commonly acids that have oxygen atoms in them. So for instance, you could have hydrogen and maybe the sulfate to make sulfuric acid, H2SO4, or it could be I don't know, the carbonate anion to make H2CO3, something like that. So oxyacids are acids that are usually polyatomic, and the polyatomic anion has a oxygen. An electrolyte is anything in solution that has a charge. So electrolytes are solutions that can conduct electricity, and those solutions are formed whenever you've got. No, it's good. whenever you've got any kind of ion in solution. So it could be hydrogen, it could be hydroxide, but it could be anything else. You could have, like if you put salt into water, you end up with sodium ions, you end up with chloride ions. Any kind of charged ion in solution allows the solution to conduct electricity. Water itself is not a conductor of electricity. Water is a very poor conductor of electricity. Pure water, in fact, we measure the purity of water based upon its conductivity. Very, very pure water is a terrible conductor of electricity. It's when you put stuff into water that is an electrolyte that increases the concentration of ions in solution that allow the water to conduct electricity. Without charged ions in solution, water doesn't conduct electricity. I'm not saying you should like try that out, but water doesn't conduct well. We have a water purification system that I use to make very, very pure water for dealing with our saltwater system, and I monitor the purity of the outgoing water by using a conductivity meter that just measures how conductive the water is. And if it's working correctly, the meter reads a value of 0. It just says the water is not conducting any electricity at all. And that meter can read from values from 0 up to 1,000. And our incoming tap water usually has a conductivity sometimes up to about 150. So tap water is about 150. And as you remove more and more ions from the water, you get from 150 down close to 0. And when the thing's working correctly, it reads 0, which is infinitely small relative to a concentration of 150 or conductivity of 150. All right, so if you did those problems, that's how the solutions go. The test for acids and bases, which is based upon the same kinds of calculations and the same kinds of concepts, we posted tomorrow. We'll have time to do it in class tomorrow. Just bring your Chromebook. And so the rest of the period today, you can work on your acid-base project, and there'll be some time on Monday as well. So whatever questions you have about acids and bases, figure them out and get them answered today. Do a test on acids and bases tomorrow, and then next week we'll do some other stuff. We're getting close to the end of the year though, huh? We've got like next week. And then there's like a 4-day week. So we have Memorial Day off. And then a 3-day week, but kind of a 2-day week. That's hot. I'm excited. All right, have fun working on your project and stuff. Bye.